was asking for. Alright, problem 1, quiz 1. Describe what would happen to the golden leads of an electroscope if you brought a negatively charged rod to the metal sphere. So here, quiz 1. Problem 1A. You're bringing a negatively charged rod to an electroscope. And if you do this, you're going to be polarizing the electroscope. The positive charges are going to be brought up. The negative charges are going on the leaves, and they will spread. The leaves will spread. In scenario B, I just had a minor change, and instead of a negatively charged rod, you bring a positively charged rod to the electroscope. If you do that, you're still going to polarize the electroscope. This time the negative charges will accumulate at the head, and then the positives would accumulate on the leaves, and then the leaves will spread regardless. In C, I just ask you to give me a scenario in which an electroscope is utilized to make the leaves come closer together. To make the leaves come closer together, you would already have to have an electroscope that is, let's say, positively charged. And then if you bring in proximity a negatively charged rod, then the positive charges would be all attracted to the sphere of the electroscope, at which point the leaves will come down. So, yeah. So that was the scenario we're looking for. And so I intended for this problem to be understood in the polarization sense, where you actually are not making contact with the electroscope. However, I did see that some of you guys interpreted it as if you were making contact. As long as your explanation was correct, I still gave you full credit, because the problem did have I would say, large room for ambiguity. And as long as you are self-consistent, you will be getting those points back, or you will still be getting those points. But this was the intended solution. Problem 2 is you have two charged particles, particle 1 at x is equal to negative d, and particle 2 at x is positive d. Particle 1 has a charge of positive q, and particle 2 has a charge of negative q. What is the force, magnitude, and direction on a third particle with charge positive q located somewhere on the y-axis? So let's first begin by drawing the scenario. This is the origin, and I said this has positive charge, and this is at negative d. This is a negative charge, and this is at positive d. I want to know if we were to place a third charge on the y-axis, except not y is equal to 0. So it would have to be some arbitrary position, let's say up here, and it is also going to be positively charged. So the electroscope, the third charge can be anywhere along the y-axis, just not at the origin right here. And so let's just work with this scenario. Opposites attract, like charges repel, positive and positive. Therefore, we're going to have from charge 1, this will be force from the positive charge. Opposites attract, so therefore from the negative, you're going to have an attractive force, and it'll be that, force from the negative. Here, you always want to approach the problem intelligently, and here we can invoke an idea of symmetry. Because the distances to the third charge are identical for these two, we know that F net y is going to equal 0. Because the upward, the y component of this force and the y component of this force will cancel. Also, we know that F, the force of the positive in the x direction, is equal to the force from the negative charge in the x direction. And so the net force in the x direction is F positive charge in the x direction plus F negative charge in the x direction, or simply 2 times F positive in the x direction. So by that, we're trying to get this component. So that's theta. This would be the Fx. To get the force, we apply Coulomb's law, which is K Q1, we'll call it QA QB over R squared, times the cosine of the angle theta, because it's the x component of it. Here, all of the charges are q, so this comes out to be kq squared over r squared. Cosine of theta is adjacent over hypotenuse. So this is also theta, and so we have this triangle to work with. So cosine of theta is equal to the adjacent, which will be the length d, over the hypotenuse, which is r. So this would be times d over r. But what is r? Using Pythagorean theorem, we know that this is square root of d squared plus y squared, where this distance is y. So when we put all those things together, then we get the net force in the x direction is 2 times kq squared d over d squared plus y squared raised to the 3/2 power. And for the full solution, I would like it to be written out in the vector form, which would be 2kq squared d over d squared plus y squared raised to 3/2 power I plus 0j. Problem 3. I give you that an electron is located at 1, 1. I want to know what the electric field are at these 4 points, 0, 1, 1, 0, 2, 1, and 1, 2. And I just give you that the coordinate system is given in terms of millimeters. So the information that I give you is that an electron is located right here. I want to know what the electric field is at this point, which is 0, 1. Oh, sorry, that's 1, 0. This point, which is 0, 1. Another point, 2, 1, which is right here. And 1, 2, which would be right here. This is an electron, so the electric field is going to be towards the electron itself. So the electric fields are all pointing towards the electron. Here we want to be approaching this problem intelligently. So we want to invoke an idea of symmetry, or maybe we'll say geometry. what is true at all of these 4 different points? You guys recognize any pattern or something?
The distance to the
Yeah, is what?
one.
Yeah, all the distances are the same, meaning all have same magnitude of E. Because they have the same distances. And using Coulomb's law, E then is going to be equal to KQ over R squared, where this is 9 times 10 to the 9th Newton meter squared over Coulomb squared. The charge Q is an electron, which is 1.6 times 10 to the negative 19th coulombs, divided by 1 millimeter, which is 0.001 meters. And if you do that, you get a value of 0.00144 newtons per coulomb. Newtons per coulomb. That's the magnitude. I actually need the full electric field. So the electric field at 1, 0, that would be here. The electric field is just pointing straight up. So this would be 0I plus 0.00144 newtons per coulomb in the J. At 0, 1, that would be over here. The electric field is pointing directly to the right. And so the electric field then is equal to 0.00144 newtons per coulomb I plus 0J. At 2, 1, the electric field, that will be over here, is pointing in the negative x direction, so it is negative 0.00144 newtons per coulomb I plus 0J. And at 1, 2, you're all the way up here. The electric field is pointing straight down, so negative y direction, so this is 0I minus 0.00144 newtons per coulomb in the J, and that would be the final solution. For quiz 2, oh, sorry, yes.
She's gonna text you when you're done. with
Who's gonna
quiz two.
text me?
No, Jess is gonna text me when you're
Oh,
done.
I'll
with quiz
text you. I was
Yeah.
like, okay, I didn't give anyone my phone. Okay, problem 1, I want you to draw this electric field lines of the following. Okay. So quiz 2, problem 1A is 2 negative charges, so you have a negative and a negative. Okay, I think you guys know how to do the net. Okay, I think the only one that actually has confusion is 1C with a dipole. Is that right? Hopefully that is. Well, this is a dipole. We went over that. And the only thing I wanted you to make the connection was, do you know to draw from positive to negative? So on here, what would a positive to negative association look like? Also recognizing the further you go out, the weaker the field gets. Then the field lines would look something like this. You're still going from the positive to negative. And so forth. There you go. That's all I was looking for. In problem 2, you're told you have 3 charged particles, one at x is equal to negative d, and a particle 2 at x is positive d, and particle 3 at x is equal to 0, all with charge of positive q. So let's do that. This is negative d, this is 0, this is positive d. There's our 3 charges. to know what is the electric field, the magnitude and direction on the y-axis. Your solution only contains the numbers and the following variables. So we want to know what the electric field is arbitrarily on any point along the y-axis. So we just pick an arbitrary point. Wait. Let's just work on an arbitrary point up here. There's no charge there. We're just looking at how these three charges are distorting the space right here. Because these are all positively charged, the electric fields are all going to be pointing away, and pointing away. Let's just call this 1, 2, and 3. What simplifications can be made before you even begin the problem? So here we'll call this electric field from 1, electric field from 2, and electric field from 3. Is there any simplifications that can be made? Zero.
The E1 and the E2 are gonna be the same.
Okay. Can we be a little bit more precise than that, or can we extract something that might be very useful out of this?
They're the same in well, actually.
Right, they are the same actually this, okay, the vectors are actually not equal. The magnitudes are equal. E1 is equal to E2, that is true.
Their exponents cancel.
Yeah, so this will lead, and we know that the angles are also going to be the same. Essentially here, all this will lead to E net in the x is going to equal 0. The x component of 1 is going to cancel the x component of 2. And from 3, you don't have any x component anyway, so you don't even need to consider it. So the magnitudes equaling are also useful because we know that E net in the y is going to be E1y plus E2y plus E3y. Because the magnitudes are equal as well as the angles, this and this are going to be the same. So this is equal to 2 times E1y plus E3y. Where E1y is E1 times the sine of theta, which is KQ over R1 squared times sine of theta. Sine of theta is the opposite over the hypotenuse, so that's going to be y over R1. So in total, this is going to be KQ y over R1 cubed. But what is R1? You use Pythagorean theorem, which is the square root of d squared plus y squared. So then E1y is equal to KQy over d squared plus y squared raised to the 3/2 power. So that gives us this guy. We're still missing E3y, so that's what we need to do next. E3y, if you look here, you only have the y component. So it is simply, you get it from Coulomb's law, KQ over R3 squared, which is KQ over y squared. And if you look on the problem statement itself, I tell you you're allowed K, Q, D, and Y. And if you go into the problem, everything is KQY dy, KQY. Now we have it in our final form. So then the net electric field in the y direction, you just add the two. You add it given by this equation, so it's 2 times KQY over d squared plus y squared raised to the 3/2 power plus KQ over y squared. And in the full form that I would like for you guys to utilize, it would be 0I plus, we can factor out a k and the q for both terms there, so it's kq times 2y over d squared plus y squared raised to the 3/2 plus 1 over y squared in the j direction. Yeah.
It's E net X instead of E net
Oh,
Y.
this should be E net, not x, just E net.
Okay.
Yeah, it's got this x component and the y component. So this was extremely similar to an example I did in the class. The third problem, essentially I ask you to carry out the checking methodology that I introduced to you guys, which is use the same scenario as problem 2, and as y approaches infinity, so you're getting super duper far away from our system now, you would expect the system to behave as 3-point charges exerting a field in the y direction. Because when you go super duper far away, the distance that separates them, that becomes negligible, and they just look like 3 charges from very, very far away. And let's see if we actually get that mathematically. And so the only thing that we're really asked to do is take the limit as y approaches infinity of our net electric field expression. So if we do that, we get the limit as y approaches infinity of 0I plus KQ 2y over d squared plus y squared raised to the 3/2 power plus 1 over y squared. When we take the limit, oh sorry, this is infinity, not 0, infinity. When we do these, we're making comparisons wherever we can. We see a parentheses here with the y, and if this goes to infinity, d essentially goes to 0. And so what we're left with is kq times 2y over y squared to the 3/2 power, where y squared raised to the 3/2 power, the 2's are going to cancel. Is that right? Yeah. This cancels with that, plus 1 over y squared. And so what you get is kq times 2y over y cubed plus 1 over y squared. There's a y here, y over y cubed. One of these cancels, this, the power to that is lowered. And now you see that these two terms have the same denominator, so you can add, and you get kq times 3 over y squared, which is simply 3 times the electric field of a point charge as we expected. Okay, Kylie is now permitted back in. Wait, actually, okay, now she's permitted back in.
But you can't.
Oh, yeah.
Can you just zoom out on?
Okay, she's not permitted back in.
I'll stop right
It's just
Liar? This is good?
Got it. Thank you.
Okay, now she's permitted. Now she's permitted back in.
Wait, I had a question though.
Alright, so everyone's taking quizzes 5, and all of you guys were here earlier today taking the quiz. Alright, quiz 5 from last week. Okay. Alright, I'll just kind of explain the problem to you guys. The first problem, I said two parallel plates are charged to have a potential difference of 500 volts. And then I ask you to answer the following. So we have a parallel plate capacitor. And let's say there's 500 volts in between. Meaning, this is 500 volts and this is 0 volts. In part A, I ask you if what is the potential energy? So U is equal to what if the electron is at negatively charged plate. So if the electron is right here, this negatively charged plate will shove us that direction. And so U is equal to Q times V. And so this electron will traverse the full 500 volts. So it will be 1.6 times 10 to the negative 19 coulombs times the voltage difference. Here the charge is negative, and the change in voltage difference would be negative 500 volts. So it's 8 times 10 to the negative 17 joules. In B, I ask you what is the potential energy if electron is at the positively charged plate? Potential energy is Q times V. However, if the electron is here, will the electron go anywhere? No, it's already at the final destination. Even though a voltage difference of 500 exists, this V is actually really asking what is the difference between the final voltage of the electron versus the initial voltage of the electron. Well, it's 0 minus 0, which is 0. So it's Q times 0, which is going to be 0. That was the answer. In scenario C, I ask you what is the potential energy if a sodium ion is at positive plate? Is that right? Oh, negative plate. Well, sodium ion is positively charged, and if it's on the negative plate, it's already at its final destination. It won't move anywhere. So, similar answer to part B, the potential energy is 0. D was asking, what? Where's that? What? How do you get rid of it?
The sign.
What? Doesn't even let me undo. Okay, D was asking, what is U if a sodium ion is at the positively charged plate? All right, potential energy is just referring to can it do anything? If it's at the positively charged plate, then the positive charge plate will, like charges repel, will push it across. So indeed, in this case, we have a meaningful voltage difference, and it will go across the full 500 volts. But what is the charge Q? Well, I mentioned this way at the beginning. A positive charge simply has an absence of an electron, so the charge is still 1.6 times 10 to the negative 19 coulombs. And so this is 8 times 10 to the negative 17 joules. So a positively charged ion has the same charge as an electron. It simply just a removal of an electron. E, I ask if electron is at positive plate, or begins at positive plate. Well, I want to know, what is the impact speed, Vf? Well, if the electron is at the positively charged plate, it's already at its final destination, so the impact speed is going to be equal to 0. It will not go anywhere. Problem 2, I ask you to draw the equal potential lines of a positive charge. So remember, equal potential lines are drawn perpendicular to the electric field line. So let's begin with the electric field lines like this, like that, that. So the general shape is going to be that of a sphere. That's how you would draw it. However, I ask you to draw 3 equal potential lines for A, one at 3V, one at 2V, and one at just V. So they're integer multiples of each other. Unfortunately, they do not have even spacing. It would have to be like this, because there is a 1/r relationship. Which one would be 3 volt or 3V, the highest voltage? The smallest one or the largest one?
The smallest.
Yeah, the smallest one, because it's closest to the positive. This one is 3V, then 2V, then 1V. Because you have a 1/r relationship, it is easier to go from 3V to 2V than it is to go from 2V to 1V, and that's why there's a spacing difference. Part 2, I ask you to draw equal potential lines between 2 negative charges. Well, let's begin by drawing the electric field lines. I want to make a line that connects the two as well as the halfway point. And the electric field lines are going to look like that. These are pointing towards and I ask you to draw one close to the charges and one close or far away from the charges. The one close to the charges will look like this. The one far from the charges, remember, we have to be perpendicular. Here, this is perpendicular, so we go like that. And then perpendicular is kind of there, so it'll curve like this. And it's going to continue to go, but for it to be perpendicular, the concavity has to change. And so it actually makes a dumbbell shape. So it actually do that. I saw a lot of people, for some reason, they drew everything correctly, except they made sure not to cross that halfway point to draw it like this, and I'm not sure exactly where that comes from, because you're breaking the rule of perpendicularity. Instead, if you're actually trying to be perpendicular, yes, over here, these would be perpendicular in that fashion. In problem 3, I tell you that two charges are on the x-axis, one at negative 26 centimeters, one at positive 26 centimeters, so this is at 0. This has positive 50 microcoulombs. This has negative 50 microcoulombs. I want to know what the electric potential is 30 centimeters above our 50 microcoulomb charge. So we want to know V is equal to what? And here we have two different contributions, which is simply V1 plus, we'll say V1 plus V2. The potential of a point charge is simply KQ over R. We'll call this charge 1 and we'll call this charge 2. So V1 is equal to KQ1 over R1, which is 9 times 10 to the 9th meters squared coulomb squared, times charge 1, which is positive 50 times 10 to the negative 6 coulombs, divided by, what is the distance R1? In this case, it's only 30 centimeters, so it is 0.3 meters. If you do that, you should get a value of 1.5 times 10 to the 6th volts. Voltage 2 is KQ2 over R2, which is 9 times 10 to the 9th newton-meter squared over coulomb squared. The charge this time is negative, so it's 50 times 10 to the negative 6 coulombs divided by the distance R2. We need the hypotenuse here. So that's the Pythagorean theorem, which is the square root of, this is one of the lengths, which is 52 centimeters. So it's 52 centimeters squared plus, I'll pre-convert to meters. 0.52 meters squared plus 0.3 meters squared. That entire thing square rooted. And if you do that, you'll get a value of negative 7.5 times 10 to the 6th, or 10 to the 5th volts. And so V then is going to be 1.5 times 10 to the 6th volts minus 7.5 times 10 to the 5th volts, which is simply 7.5 times 10 to the 5th volts, and that's the final answer. Any questions on this one? All right, now for the quiz that you guys took today. Question 1, you have a capacitor with capacitance 100 microfarads. So I told you C is equal to 100 microfarads. The first one, what would the total charge of the capacitor be if 9-volt battery was applied to the capacitor? So Q is equal to CV, meaning it is 100 times 10 to the negative 5th farad times 9 volts, which is equal to 9 times 10 to the negative 4th coulombs. Problem 2, I ask you, what would the capacitance be if you replaced 9 volts with AAA battery? And I told you that the AAA battery has a voltage of 1.5 volts. And the answer, I gave you the answer at the very beginning. The capacitance is 100 microfarad. Nothing changes. Yeah, question.
Is that 10 to the negative 6 farads? for microfarads.
Oh, yes, this should be negative 6, yes, that's good. And so in problem 2, I already gave you the solution. This is where most of you guys would charge me with asking a trick question. This is not a trick question because I made a large deal that capacitance is a material property. It doesn't matter what voltage you apply, if you change the voltage, ultimately this is going to result in a lower Q. The capacitance remains the same. The capacitance is how the capacitor was built. So if you think it's a trick question, unfortunately this is how I understand if you actually tried to understand, or if you actually understood versus just memorize the equations. So for me, it is not a trick question. This is an extremely valuable way of actually determining various things. Problem 2, I literally copied and pasted this from the problem set. It's like this. I want to know what the equivalent capacitance would be. First thing to recognize, well, let's just label these 1, 2, 3, and 4 accordingly so we can talk about them. One thing to recognize is that 1, 2, and 3 are parallel. So we can reduce this down to 2 capacitors where this is C1, 2, 3. And this would be C4. Then you can see that these 2 capacitors are clearly in series, so we can reduce this down to a single capacitor, C1, 2, 3, 4, and this is the capacitance that we are concerned about. Well, for parallel, we know that this is simply the sum of the capacitances, so C1, 2, 3 is going to be C1 plus C2 plus C3. And I told you every single capacitor has a capacitance of C, so this is equal to 3C. Here, 1, 2, 3, and 4 are in series. And in series, so 1 over C series is equal to the sum of 1 over Ci, which is going to be 1 over 3C plus 1 over C. To be able to add, we want the same denominator, so we multiply this by 3 over 3 so that the denominators are the same. We have 3 over 3, at which point you're going to get 4 over 3C. And that's what 1 over C, 1, 2, 3, 4 would be equal to. Well, I don't want 1 over C1, 2, 3, 4. I just want C1, 2, 3, 4, which is 3/4 C. And that was the final solution. Okay, I apparently don't know how to count to 3. Except I did. You guys should thank me. There was 4 problems. I actually got rid of 1. And then I forgot to change the number. So that's what happened. Alright, so don't make fun of me. So problem 3, except I labeled it as 4. I tell you a speaker is operated by a 9-volt battery. If the maximum current that the speaker can withhold is 1.2 amps, but the minimum current that you need to actually turn on the speaker is 0.8 amps, I want to know what is the range of diameters of copper wire that can be used. So one thing we know is that Ohm's law, V is equal to IR. Also, we know that the resistance of wires can be given in terms of the resistivity times the length divided by the area. But I didn't ask for the area, I asked for the diameter, which is rho L. The cross-sectional area, you can get it in terms of the diameter, which is pi over 2 squared. So from here, we can get, let's say the maximum value of R, resistance that we can have is V over I min, which is 9 volts over 0.8 amps, and that's going to be 11.25 ohms. So this is the maximum resistance that we can have. The minimum resistance will be V over the maximum current, which is 9 volts divided by 1.2 amps, which is going to be 7.5 ohms. So from here, we just compute what is the diameter that corresponds to these two resistance values. So from here, we can isolate for the diameter D, at which point you are going to get 4 rho L over pi times the resistance square rooted. Which is going to be the square root of 4 times, I gave you the resistivity, 1.68 times 10 to the negative 8 ohm meter, times the length, which is 1 meter, divided by pi, divided by our resistivity value. And you would plug in the two resistances into our equation, and so then the diameters you're going to compute are 4.36 times 10 to the negative 5th meters and 5.34 times 10 to the negative 5th meters. And that would be the range. So the smallest you can have is 4.36 times 10 to the negative 5th. The largest you can use is 5.34 times 10 to the negative 5th. And with that, I will see you guys tomorrow.